Hi everyone, we're going to get started in just a minute. Well, it is officially 12 o'clock. So hi everyone and welcome. Thank you for joining today's webinar. I'm with Levine Electronics and Electric, or L3, a manufacturer's representative serving the Southeast. We are proudly known as the experts in electrical controls, power distribution, and protection across our territory. From power quality solutions and transformers to arc flash and ground systems, this is the foundation of what we do best. We work alongside our sister company, Power Plus Controls, a specialty electrical distributor that specializes in helping customers track down those hard to find products, finding better lead times and innovative designs to help solve every problem. At L3, our business is built into two key divisions, control and automation, and medium to low voltage distribution and protection. To learn more, please visit our website at l3.com, where you will find our line card, company directory, helpful tools, and a library of over 100 educational videos. If you have any questions during today's presentation, please put them in the chat or raise your hand and we will turn on your mic. About 2 hours after the presentation is over, you will be emailed a certification of completion. If you do not receive a certification of completion, please email me at Sarah, S-A-R-A-H, at l-3.com. Today's presentation is being hosted by John Levine, the founder of L3. Without further ado, let's get started.
Thank you, Sarah. Appreciate that. This is a really fun presentation, so I hope you enjoy it. I started off and I actually picked this slide. Let me grab the pointer because I'm a pointer kind of guy. Laser pointer. Okay. As you can see, this kind of looks like chaos. And when I think of harmonics, that's kind of what I think about is harmonics. Today's presentation is on power quality harmonics and IEEE 519. It's an extremely misunderstood topic. Hopefully, after I get done with this, we can quote Paul Harvey and say, here's the rest of the story, and you'll have a much better handle on what harmonics is all about. My agenda today, I've got broken down to 8 different parts. First, I talk a little bit about power quality. It's a lot more than just harmonics. Then I go into what are harmonics, what are sources of harmonics, are harmonics a problem? That's the million-dollar question that I've been asking for a very long time. I'll then talk about IEEE 519, 2014 and 22. The 22 is now the standard. 14 was a recommendation. We'll talk about that. With transformers, and we do a ton with liquid and dry type transformers. Everybody talks about K factor with harmonics. So I'll give a little explanation of what K factor is. And then I've got 3 different methods you can use to correct harmonic issues, and then a conclusion. So without that, I'll get started. So what is power quality? I've actually listed here 9 different types of power quality. It could be something that's voltage dips, sags, brownout, interruptions, swells, harmonics is just one small part of power quality. Fluctuations of flicker, voltage unbalance, transient, and frequency deviations. I actually am a visual guy, so I actually like to do it this way. So here's a picture showing over and under voltage. As you can see, if the voltage should have been somewhere in between these two, this is under, that's over voltage. Harmonics we'll cover in a lot more detail. Flicker, we've all seen our lights flicker. It's actually an interesting phenomenon. What I found out causes flickers a lot of times with electronic devices, especially 3-phase devices. They actually have 2 of the phases shorted out at the same time, and that causes the flicker to occur. I've actually got a white paper just on that if you want more information on that. Unbalance is a real problem with power quality. People don't realize it, and I had 2 plants side by side. One had all kind of motors burning up, the other didn't. It turned out it was unbalanced. If you have unbalance, you're going to have voltage between these 2 phases, And bottom line, that causes what we call negative sequence current, which is running the wrong direction, which is not a good thing. And I'll talk more about that. Sags is when we have dips. Swells is when we got overages. Transients is also a big problem. Interruptions and frequency. So those are just some of the different areas that you can get into with power quality. So now the next question is, what are harmonics? Harmonics are created when we switch on and off electronic devices and we don't use the entire sine wave. And it can be done by diodes, SCRs, or even devices like IGBTs. This is what drives use IGBTs. I always like to show the full wave bridge rectifier and how it's actually designed. So with a full wave bridge rectifier, we take the sine wave like this, and we basically make it two humps like that. And the way we do that is, if I think right here and I go the positive side of the sine wave, positive side is going to come up. And as we know, diodes only let current go through one way. Since this is the positive side, it won't go this way. It can only go this way through the funnel. And then it can go to the load. From its load, since I'm still talking the positive, it comes around here. And then where's the positive go? It's going to go down through this funnel. And then it goes back to the source. Likewise, when I go to the negative part of the sine wave, the negative now can't go this way. It's going to want to, excuse me, let me go this way. The negative is going to come this way. It's going to go up through this diode, because now it's the top part, come through here, go back here, and then go back here and go back to there. So that's kind of how a diode works. We also are all probably familiar with SCRs. With an SCR, that's your light dimmer in your dining room or your bedroom or your wherever you've got it. But basically what we do with a light dimmer is we basically just decide we have a certain amount of voltage before the SCR turns on. And so that's how we get simple, lower voltages. But obviously that you're chopping up the sine wave, and that's a problem. And then I grab this. Here's showing a normal sine wave. A lot of you have heard of MOSFETs. This is what you get with MOSFETs. IGBTs is what we use in the drives, as I talked about. I've actually got another slide that'll show it better than even this. But in that slide, I'll actually show how we have like 2,000 of these positive and negative signals within a cycle. And that's how we create, and we form it to form a sine wave. And here's what a GTO looks like. So that's just some of the different things that are causing harmonics. This is an interesting slide that I've got. So what I've got here in the yellow, that's our fundamental frequency, okay? And then what I've shown is a third harmonic. And so with harmonics, it actually occurs in the same time period as the fundamental. But a third harmonic, I'm going to have 1, 2, 3 cycles in the same time that I've got this one harmonic or one cycle. So let me ask you a question here, and you can put your answers in the chat. I'm showing this as 20 milliseconds. We're in a 60 hertz system, right? So one cycle is 16.66 seconds. Why am I showing 20 milliseconds instead of 16.6? Can anybody put that in the chat and give us an answer? Anybody answer? Oops, let me open up my chat. No answers that I see in the chat. Come on. What do they use in Europe?
Someone
In Europe,
responded with the third order.
the third order? Okay, in Europe, what do they use? They use 50 cycles. So I'm actually showing a 50 cycle system. So in a 50 cycle system, one cycle would be 20 milliseconds. So this is a good example of how the Europeans actually do a better job than we do, because it's a lot easier to figure out one cycle. 5 cycles is 100 milliseconds. One cycle is 20. So they actually do a better job than we do with our 16.66. So then what happens is, since we've got harmonics and I've got the fundamental, what happens is when you add these together, you get this distorted waveform. So you see how this is positive and this is positive, so that puts it way up here. If I go to this peak of the fundamental, it's here, this one's negative, so it actually brings it down. So when we get into harmonics, this is why we get all these distorted waveforms, because we're combining all these different harmonics. Okay? So my question to you is, what's the blue line? And here's the answer. The blue line is actually a third harmonic. Okay? Here's just some different examples of harmonics. So a lot of you may have heard of a 6-pulse rectifier. I think of this as like rabbit ears. So if you're actually looking at a waveform and you see these rabbit ears, that's actually a 6-pulse rectifier. Here's what a 12-pulse rectifier looks like, and this is what a 24-pulse rectifier looks like. See how smooth this 24-pulse actually is? And the way they achieve this is by what, and I'll talk more about this in another slide, is they have transformers. Oh, let me go back and put where's my pointer? Do my pointer back. Laser pointer. So here you see these transformers. What we do with these transformers is we got transformer in front of it, and we do a phase shift. By shifting the different phases, you can actually cancel out the harmonics. And that's what they're actually doing in a 24-pulse rectifier. This slide came from a company called PMI. They probably, of everybody I've seen, do the best. I subscribe to their webinars. They're a company that makes meters and sells it primarily to the utility market. So they really have some great presentations. So what you've got is all the different harmonics. If you see the first, fourth, seventh, any of them that's a multiple of 3 plus 1, that's positive sequence. Positive sequence, if you know anything about symmetrical components, is good, because that's what we want. We want positive sequence. Negative sequence is going the wrong direction. So negative sequence is fighting against what the rotation we want. And that's all the multiples of 3 minus 1. And then we have zero sequence. Zero sequence is all the current that's going through the neutral or the ground. So we hear about people burning up neutrals because of harmonics. That's because we've got zero sequence current. There's also a subset of the zero sequence current called as the triplets. And the triplets are the odd multipliers of 3, and I've got another slide on this, but that would be 3, 9, 15, 21 would be those. So the positive rotate with the fundamental, which is good. The zero sequence do not rotate. And then the negative, that I kind of mentioned before, where I had different voltages on 2 phases, those are actually rotating against the fundamental. So that's bad. Here I'm just showing the triplet harmonics. So as I mentioned, those are the third, ninth, the odd ones. And that's where we get the zero sequence currents and voltage from the triplets. That's causing the overvoltage we talked about in the neutral. Okay? So when people ask you that, that's what it is. So let me ask you a question. If the third harmonics is 180 hertz, because it was 3 times the 60, what frequency is the 50th harmonic? Sarah, do we have any answers?
Not yet.
What's 60 times 50? It's 3,000. So with 3,000 hertz in that 16.66 milliseconds, I'm having 50 of those cycles. So it comes out as like 0.334 milliseconds per hertz. It's extremely fast, just for trivia for you. Okay. There's also a thing, and this they refer to IEEE standard 61004-7 called, and this is just so you're aware of it. Whoops, just lost my screen. Came back. Good. Called interharmonics. So these are all the harmonics that are between the normal harmonics. So here I've got the third, the fourth. Here's the interharmonics that are in between it. And those are actually harmonics that could be created. And when we get into some analysis, we may need to actually go into the interharmonics and look at them. Okay? Any questions at this point? So let's look at some of the sources of harmonics. So obviously we talked about variable frequency drives, VFD, Those are a great source of harmonics. DC drives can be a source of harmonics. UPSs, anything that's got electronics in it. Arc furnaces are terrible for harmonics because they're destroying the sine wave. LED lighting is a real issue in some applications. And then battery and EV chargers. So that's just 6 examples of where you may have harmonic issues. So now we come to the million-dollar question. Any questions at this point? Are harmonics a problem? And this is an age-old question that I've been struggling with my life. So the answer is harmonics are not a problem. Okay? Until they are. And that's a quote from Chris Vance of Levine Electronics and Electric. I think it's extremely well put because you don't know if harmonics are causing a problem or not unless you do a complete analysis of your system. So, and we have that capability. So, you know, as I said, this is a million-dollar question. The best way to look at this is first look at the power triangle. And I gave you all a teaser that I said I was going to explain to you why I don't think the power triangle is right. In fact, I know it's not right. So I'm going to show you that now. So the electrical engineers that are on the call, you'll definitely get a good laugh out of this one because they never taught us about this. So let's just talk about the power triangle. Okay, we know that kW does real work. kVAR is either inductance or capacitance. And then when you add them together, we have our displacement kVA. Very simple. The beauty about reactance is it's always 90 degrees to the kW. So it's either, if it's kVAR, it'll be this way. I mean, if it's capacitance maybe, and if it's an inductor, it'll be the other direction. So that's why when we have motors, and here's a good example of this. This line here is the voltage. Here I've got the current, and what is it, leading or lagging? Can anybody answer that question? Put it in the chat. Right now you see the current is lagging.
I have a question, John.
Go ahead.
It's from Jay Johnson. I have seen harmonic issues in the data centers with AI loads. Is that UPS related based on simultaneous harmonic loads? Question mark.
Yeah, that's caused by electronic devices because they're switching. Electronics is where it's caused. And it's interesting in data centers because we have 3-phase and most of the computers are single phase. In a lot of applications, except for the HVAC drives for all the cooling, but on the computers themselves, a lot of that cancel each other out. So most of what we're seeing in the data center is really coming from the drives that are controlling all the chillers. Mm-hmm. So, but here I've got an example of voltage, and the current is lagging the voltage. Okay, and it's by 90 degrees. So, and because of that, you have what's called power factor. And power factor is kW over kVA. And of course, what do we do when we have a motor's an inductor? So how do we correct it? We add capacitance. So when we add capacitance, we can lower this, gets this kVA closer to kW, so we make a more efficient system because we're lowering the amount of current. Okay? And here's the million-dollar point. Let me ask a question here. In kW, are there harmonics? Anybody want to guess? Y'all are a quiet audience. I can tell you.
No, they are not. They are blowing up our chat.
They're blowing up the chat?
The answer that everyone's giving right now is no.
That is correct. There's excellent. So there is no harmonics in kW. Are there harmonics in kVAR? Does the capacitor or in reactor have harmonics in it? Answer is no. So therefore,
we got in the chat is yes.
And that's wrong because they're not. Okay. So because of that, that's why I call this displacement kVA. Because right here, there's no harmonics shown in this picture. I'm the GE multi-lin rep. And when you set up a multi-lin relay, I can either set it up to look at the fundamental, or I can look at RMS. Sarah, can anybody tell me what the difference between fundamental and RMS is?
We'll give everyone a second to answer.
Any answers?
Not yet.
RMS includes harmonics. So how can I have this showing both fundamental and RMS? I can't.
Well, I did get an answer. It is 1,732.
Okay. So all I'm showing here, there's no harmonic shown in this equation. The way we really should show the power triangle is it's actually a three-dimensional equation. So here's kW, here's kVAR, and this we call displacement. And this is showing the harmonics. And after I get through with all these have voltage, in one of the slides I'll actually simplify it down to current and show you the difference. But so here's your displacement kVA, and here's your real total kVA, which includes the harmonic component. Why they never showed us this as engineers, I'm shocked, because this is really the true equation. When I saw it, it blew my mind. Okay. What's interesting here is if you look at this, and I'll show this more detail in another slide, but I'll look at the power factor, which is kW over kVA right here, because this one's going further away. I'm always going to see this total kVA power factor lower than the displacement kVA. And there's actually a paper that says, if I know both these kVAs and I know this power factors of these two, then you could actually calculate what your harmonics is, which is kind of interesting. And here's our formulas for this. I had to give you a little math just to make this worth your while. So the displacement power factor that I was talking about is the P over P squared plus Q squared, okay? Which in P squared plus Q squared is going to be the kVA. True factor power factor is P plus Q plus D, and that's your total. So because I've got this D component in here, I can always say that the true power factor is going to be lower than the displacement power factor, okay? And power factor like THDI, which I'll talk more about this later, is always could change. So I wanted to just make you aware of that. Okay, and here's all our formulas. So, you know, because I've got voltage in every one of these, I can actually eliminate the voltage and just shows current. And if I just show the current, here's your active, your reactive, your harmonic current, the fundamental, and the RMS current. Okay, so that's how you actually see all the different, and the real power triangle, the way it should be shown. Going back to Pythagorean's theorem, obviously displacement is P plus Q, the total is P plus Q is D, and D is displacement. You also can get, when we get into active harmonic filters, they also call them dynamic filters. What we're doing is we're going to take the active and we're going to subtract and cancel out part of the reactance and the harmonics and get rid of all that so you can improve it, is how it's actually set up. And we'll talk more about that. Okay. So how does an active filter or a passive filter work? The way they're doing is we're actually reducing the harmonics, canceling out some of those, and canceling out some of the reactives. So I'm actually bringing this power factor somewhere down in here, which would be closer to the fundamental. So that's what we're doing with filters. Okay. Any questions so far? All right, let's talk about IEEE 519/2022. So this is a new standard, okay? 14 was a recommendation. And the way you can tell a recommendation from a standard is a standard will use the word shall. A recommended practice will use the word should. So 2014 was a recommended practice. 2022 is a standard, meaning you should follow and you're supposed to follow the standard, okay? So they toughened up the standard. So here's some definitions we need to talk about. And I'll talk more about these in further slides. But the first is what we call the point of common coupling. IEEE 519 does everything based on the point of common coupling. So that's the point where you meet your neighbor, okay? And what they're trying to do at that point is they want to make sure your voltage isn't low to cause the current customer next to you to have issues with, if the voltage goes down, the current goes up. So you're not going to create current issues with the customer. So this is the PCC, and I'll show more on that. We're going to talk about total demand current. And this is how we're using to what we call TDD, which is how much current is in the system versus THDI. And I've got a better slide on this. But this is what they're now using in the standard to determine it's a reference point. THDI is the instantaneous harmonics over the current, okay? So there's a picture of that. And then TDD, this is what the new standard refers to, and they want you to compare everything to TDD. THDI can come up as a big number, where TDD should always be more realistic. And then SBR is the short circuit ratio, so that's our short circuit current over the maximum load. And we'll talk more about that in this, and I've got an example of this. So let's talk about the point of common coupling. So the point of common coupling is where you meet your neighbor. So in this case, these two neighbors, A and B, are meeting right up in here. So that's the point of common coupling here. Companies C and D, they're meeting down here. So this is their point of common coupling, okay? So this is what I don't like about the standard, is the standard is only referencing everything to the point of common coupling. All the consultant engineers I work with, they say this drive must comply to IEEE 519, but they're talking some point down here. The standard doesn't tell me what to do down here. The standard only tells me what to do up here. And I really, when I first read this standard, was really mad, because all they cared about is how you're affecting your neighbor. We want to know what's happening down here in the plant. And the point of common coupling doesn't do any of that, okay? So in IEEE 519 clearly specifies the limit given are based on the assumption that all technical justification at the PPC between the system owner, operator, and user. These assumptions, and therefore the limits in this document, are not necessarily valid at any other point in the power system. For this reason, the limits given in this document are not intended to be used for the valuation equipment. And the problem is, we want to clean up the harmonics down here. I don't really care about my neighbor necessarily. So that's where I really have a problem with the standard. The good news is they are supposedly working on that. So that'll be hopefully an improvement in future editions of IEEE 519. Okay. So what the standard has done, and they didn't have this, I don't believe, in 2014, is they want to look at the maximum load current, and they want to look at over a year's period. So what I'm showing down here, these brown, that's your actual load. This orange line is the maximum demand for a month. So if I actually counted these, I've got 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what they do is they take these 12 and they come up with a maximum demand. So they just add all 12 of those maximum demand by month divided by 12. And this is the reference point they're going to use for the maximum demand load current. Okay. And what they've done now in the standard, which is good, is they base everything on the total demand distortion versus THDI. So a lot of customers and a lot of my competitors, they'll go, oh, you got 40% THDI. The reality is I don't care, because THDI is based on what your total of your harmonics are for the 50 harmonics over the fundamental current. So in this case, you know, my demands are very high and very close, so I is going to be a large number. If I go to this section right here, this current's very low. The harmonics are going to be fairly constant. So I'm going to get a very large THDI, and it's going to give me a false positive. The beauty is, since they've gone to the new standard, they're doing it over the demand. Now I'm looking at it whatever the harmonics are over this number versus this number, and I get a real reading and a much more accurate representation. So a lot of times when customers tell me they've got a 40% THDI, I don't care because I don't know what the I was, what the full load fundamental current was. Okay. For greenfield projects and stuff, they've got things in the standard. If you don't have a year's worth of data, which most people don't have, you can do it over whatever time period you have, or you can do a projection over 30 or 60 minutes. So that's what TDD is versus THDI. Very important concept. All right, now let's talk about the standard. There's two tables in the standard. The first one relates to voltage. And for voltage, because what happens is if I have lower voltage, I cause greater current, and that's what they really care about is the voltage at the end of the day. They're not as concerned about the currents. And for voltage, we're looking at two things. There's a weekly 95 percentile, and I'll show you this in the report. I've got it in here. And that's based on 10-minute values, okay? So they have to be less than the value given in table 1. And then there's a daily, which is a short time, which is a 3-second rating, which has to be less than 1.5 times the value given in table 1. So here's table 1. Most of the systems that we are involved in are 480 volts. So the individual harmonics have to be less than 5%, and the total distortion has to be THD has to be less than 8%. So when we look at the chart that I'm going to show, you'll see 8 and 12. 8's going to be the 95 percentile, 12 will be the 99. So these are where the voltage limits are. Okay? Any questions? Now let's talk about current. So current, the way we determine the currents is we're going to look at the short circuit over the full load current. And basically, this is going to tell me how stiff my system is. If I have a very stiff system, the voltage isn't going to drop as much. If I've got a very weak district system, that voltage could fluctuate greatly with the current. So the example I'm going to actually show in the next slide, we're going to end up in this 50 to 100, and we're going to end up with a TDD of 12. But I'll show you that in the next slide when I do it. Here, this THDU, U stands for voltage. That's the European nomenclature. And that was that 8% I showed in the previous slide. Okay. So here's what we got to determine. And different harmonics have different levels that they allow per the standard. And the short circuit ratio is the difference between the short circuit current and the max current. So, any questions? So in this example, I'm actually using the meters I use for all of my analysis is from a company called Elspec that we represent. They do a lot with power factor controls, do a great job for us. They actually use SCRs for doing it so the capacitors last forever instead of contactors switching in and out.
We actually do have one question, John.
Go ahead.
Can you talk about how stiffened voltage systems are allocated voltage functionality? Functionation?
I'm not sure I understand the question.
Can you talk about how to stiffen voltage systems to alleviate voltage fluctuations?
Oh, okay, that's easy. Put a bigger transformer in there. Don't load it as heavily. You know, if you have a transformer, and depending on what, I mean, we could have a whole discussion on transformers. We do a ton in transformers, liquid dry, cast coil. But basically, you know how most of our transformers are 5.75% impedance. Some applications, because they want to limit fault currents, they'll go to like a 10%. All of a sudden, my regulation drops when I get into those systems. So the lower I can keep that impedance, the better. And a lot of times you're just loaded at 100% of the transformer and you need a bigger transformer if you can put it in the application. And that'll stiffen the system. Or diversify the load, put it to another bank so you take some load off a transformer. Okay?
John, you can also, with Elspec, they have products that allow you to have quick recovery of voltage dips and things to help you have an overall stiffer system.
Yes, that's for voltage dips. But, you know, this kind of report that I'm doing here, I need to look at not just a momentary, but more continuous. So in this case, my short circuit current, I had to manually put in from our analysis of the single line was 32,000 amps. The full load current, the system calculated was 460. That gave me a number of 71. And if I go back here to my 50 to 100, that's 71, which is a fairly stiff system. I got a TDD of 12, and that's what I'll use in my report. Also in this report, it was interesting, my voltage daily passed and my voltage over the time range passed. So all my voltages turned out to be good. What didn't pass was my currents. So my currents didn't pass in this case. I also got some bonuses. We actually had 2 voltage steps that we recorded on the system, which I can give you on this also. So this is like a summary sheet that I put out when I generate the report for my customers. And then this is actually showing the actual current harmonics. Since the voltage passed, I didn't add those. But if I go here to this one that failed, so here's the 95%, which is the 12 number I told you about. The 99, which was the 3-second rating, we can go 1.5. That's the 18 number. In this case, we failed pretty bad. 100% is passing. So we were down in the 14% range. Now the 7th harmonic on the 99 percentile, the 3-second, that was fairly close. You know, it was 87, 75. But in this case, we failed on the 5th harmonic, 7th harmonic, and the 11th harmonic. And the rest of them passed. I've had some reports I've run, and the 37th harmonic didn't pass, which is really strange. And this is where you kind of got to make a real determination of, you know, do I take care of the issue or not? But, you know, we can give you the data. If you want to solve the problem 100%, comply to IEEE, we can do that for you. Okay? Any questions on that? The way we do it when we do this, Carlin Boswell made me add this slide. What we'll do is we'll first analyze your single line diagram. Then we in turn where to install the meters. Ideally, I'm going to put them at the PCC, point of company common coupling. We can rent you the meters. We've got 13 meters, so we got more than you'll ever need. We're actually using this pure BB portable. Comes in this nice carrying case. If it's a low voltage system, I've got Rogalski coils. So we can use the Rogalski coils and put it right around it. If it's a medium voltage systems, these Rogalski coils are not designed for high voltage. So I'm going to need to get to the secondary, and I can use a clamp-on ammeter and plug that into the meters. And we're measuring both the voltage and the currents. So we can rent you the meters. We can assist you with the installation. I'll supervise it. You're going to have to have an electrician actually do it, and we only do it if the system's de-energized to install these meters. Then we'll download the data to our analysis tool, and then we can give you a comprehensive report of the data. And then we can also, and I'll show you this in the next slides, suggest how to mitigate the issues if they exist. And I've got 3 recommendations for that. Okay? Any questions? All right, let's talk about K-factor. What's K-factor? K-factor is when we know there's harmonics in the system, we need to design the transformer for it, okay? And K-factor is an index of its ability to withstand harmonic currents. And I'll talk about this in a future slide, what's really going on with harmonics. But the common K-factors per IEEE are 4, 9, 13, 20, 30, 40, and 50. I borrowed this from an ABB white paper. They skipped the 9th, but it's probably about 50% harmonics. So K1, little or no harmonics. K4, a lot of times when I'll specify a transformer, I'll tell them I want a K4 by default. And the reason for that is the difference in cost between a K1 and a K4 is almost none. And that'll get me up to 35% harmonics, which is good. K13 is 35 to 75. So K9 is probably 50%, and that somewhere in between these 2 numbers. K13, I don't see that often. K20, I rarely see, and K30, I don't think I've ever seen. So this is the different standards. So for consultant engineers online, if you want to specify a K factor, you could do that. And here's the standard. Don't specify K7 because it's technically not a standard. Okay. And these all fall under C57110. Okay. So this is what this is all about. So transformers are designed to run at 60 hertz. And what happens is that's all great and wonderful. But if I've got 50 amps at 60 hertz, I may get a 10-degree C rise in the transformer. That same 50 amps, if I'm running that at a third harmonic, can cause anywhere from 25 to 30 degrees additional rise in the transformer. Why is that? Because the higher the frequency, the more skin effect it has. So the current wants to travel closer to the surface of the conductor. Here you can see a fifth harmonic is generating 25 times more heat than a first harmonic. So that's why we need to tell the drive manufacturers, the transformer manufacturers, how much harmonics is in the system, okay? The question I keep getting is, you know, do I need harmonic mitigation for my transformer if I have a harmonic, or do I have a harmonic? I like to take a look at the load. If that transformer is 90% loaded, yeah, I probably need to get some kind of harmonic mitigation. If I'm 40% loaded, well, maybe that additional heat's not going to affect the system and I don't need it. I've got a job and the transformer's loaded 20%. My recommendation to the customer was, you don't need harmonic mitigation because you're so oversized to begin with. Of course, he chose to go ahead and put harmonic mitigation anyway, which is fine because I'll be glad to sell him the equipment. But my recommendation to him was, you don't need it. All right, let's talk about methods to correct harmonic issues. The first is phase shifting transformers. And I'll have a slide on that. Then we're going to talk about active harmonic filters and then passive harmonic filters. So a phase shifting transformer, what we do is we actually can change, and if you've ever specified transformers, you'll see like DY1, DY5, DY12. These are different angles that you're changing the secondary frequency angle from the primary, okay? So DY5 shifts at 150 degrees. So with phase shifting transformers, what the recommendation is in your building is you buy somewhere DY1 through DY2, DY3, DY4, DY12, all the different numbers, and then you stick them in different parts of your plant. Well, that's great. That's definitely going to help some of the mitigation, just like I showed you on the 24 pulse rectifier. But the problem is they're all over the location. One location may have harmonics, one may not. So you don't really know what you're getting and whether you're complying with IEEE 519 or not. Most likely you're not. This is also a very expensive solution, and I don't recommend it to anybody. It's not a good solution, in my opinion. But I do have one customer that specifies it. The second is an active harmonic filter. And that's very easy to understand because this has just like canceling headphones. So whatever harmonics I've got being generated, the automatic cancels it and you end up with a beautiful line current. And in this case, what's interesting about an active harmonic filter is this actually in parallel with a load. So if something happened to my load, I could to my filter, I could disconnect it. I'm still running, have no effect on the system. So they're really nice from this standpoint, okay? And that's like phone canceling headphones, noise canceling headphones. So it's a great solution, but it's more expensive than passive filters. But it works, it's gonna truly give you perfect, cancel out all the harmonics. What's a bonus of this is because I've got capacitors in here, I've got one application right now. When we did the study, it turned out we had 0.6 power factor, terrible power factor. Well, if I don't need to use all the capacitors for harmonic mitigation, I can actually use it to correct power factor. So the beauty of active harmonic filters is I can use it for power factor correction and I can use it for harmonics. On this one application I was referring to, we decided to use about half of it for harmonic mitigation and half for power factor. We got the power factor up to 0.97 and then use the rest for harmonic mitigation. So that's a real nice feature that you can use with active filters. Here's an example. This is actually down at Hartsfield Airport, where I've got 4 of my ComSys active harmonic filters, and this is what the installations look like. And they just sit there and run, and they've cleaned up the system dramatically, both from a power factor standpoint and from harmonics. So that's what it would look like, very clean. So how does a passive filter work? A passive filter, you may have heard of high pass filter or low pass filter. A harmonic filter is what we call a low pass filter. So it's going to block the higher frequencies. But this is something that's in series with the system. So it's going to go in line with between the drive and your power system. It also has capacitors built into it. So you are going to get some possible power factor improvement. But because this is in series, you'll see 3 and 5%. That's how much voltage drop I'm going to have across this filter. So if I've got a weak system and I don't have good voltage to begin with, that could be a problem. Okay, they obviously cost less than an active filter. And I can use this, typically I use these right by the load, individual filters, and then I use the automatic filter, harmonic filter to kind of clean up the whole system so I don't mess up with my neighbor. So you can use a combination of both, okay? Just so you can see some pictures, we represent MTE. So here's some different pictures of different harmonic filters they make. And I'm going to show you kind of graphically what all this is about in the next slide. And here I am at the next slide. So, come on. I probably got to get out of the, I got to get rid of my pointer. How to get rid of my pointer? Okay, now I should be able to get into it. Okay, so this is the demo that I've got, and we'll begin. And what's nice about this, here's your nice current, here's your voltage. If I have no VFD, as soon as I add a VFD to it, okay, you can see I'm getting notching on the current. And I can do a line side simulation. And so here's what the current's doing from the VFD that's feeding back into the system. So with no filters on there, this is what you got, okay? I can also, how much load, I can adjust that, but basically, it doesn't affect it a lot. High harmonics, 85%, doesn't comply with IEEE. Now MTE makes 2 different filters. I can put an RLW, and that'll clean it up some. I got the harmonics down from 85% to 30 to 40%, but I'm still probably not complying with IEEE. And then they've got what they call the matrix AP filter, which is IEEE certified. And that, for the load, is cleaning up the harmonics enough so I'm less than 5% harmonics. Actually, the new standard is 8%. So the 5% is a little misleading. It used to be 3 and 5, now it's 5 and 8, which I kind of showed you in the presentation on harmonics. So that's your solutions on that. Since I'm here, I'll go ahead and remove that, switch to the load just to show you what's going on the load. So on the load side, even though this presentation wasn't designed for that, I want to show you. Here's a VFD. So you remember I was talking about IGBTs? We're literally creating this voltage to create a nice line current waveform. But what happens is, depending on the length of the cable, we'll just go 33, you got what they call common mode voltage and common mode current. What happens is the longer the cable is, then I've got capacitance between those cables, and you're actually creating voltage spikes. So you need to go in there and clean those up and clean up those current spikes. Remember when we first started selling motors with drives, we'd burn up the motors because the motors were seeing like 2,000 volts and the insulation on the motors wasn't designed properly. Now all the VFD motors have higher insulation rates just to handle that. And MTE's got 4 different types of filters, DVT, filter. This is good for up to 1,000 feet. Less than 1,000 feet extends the life of the motor. No common mode voltage attenuation. Expensive VFD cables recommended. Go to the Century product. You can see that really does a good job. So depending on your length and what your application is, you can go to something like that. The sine wave Guardian, that's cleaning it up even more, reduces motor heating, motor noise. And then the Cadillac is the Nexus, reduces audible noises. If you've got an application and you're having issues in your plant, there's an excellent video that MTE did with plant engineering that I can send you a link to it. We had a conveyor company, and we actually got to put all the different products in there and test it and give all the results, and it's incredible the results we got from that. Okay, any questions on that? Okay, back up. All right, so in conclusion, I know you're waiting for that. I hope you found this presentation informative and learned something from it. Harmonics are extremely misunderstood and hard to determine. While the IEEE work is working on 2022, it only addresses the point of common coupling, which I don't like. We need guidance inside the plan, and hopefully in the future we'll get that with pieces of equipment. So I want to thank you, and I want to give some credit to some references that helped me create this presentation. ComSys does a fantastic job on active filter. They're the ones that I actually learned that the power triangle was wrong. Blew my mind because I've been doing this a long time. But they're extremely knowledgeable when it comes to harmonics. MTE obviously does our passive filters. I mentioned PMI. If you aren't getting their daily webinars, I strongly suggest you do. They do a great job. We represent several lines of drives, Danfoss being the primary one, so we can help you with presentations and topics in there. And then I have this standards for IEEE 519 and 1250. So that is the presentation. And I can now open it up for questions. If you want to raise your hand, we can unmute you and you can ask the question that you've got.
Great job, John.
Thank you, Carlin. I appreciate it.
I can't ask a question, I don't think, because I'm an organizer, but
you can ask it. We can hear you.
Something I'd like you to touch on is you mentioned the active filters are in parallel. So talk about the sizing differences and kind of how you would size that. And then the other thing is, if I walk up to a power meter and I see power factor and KVA, how do I know if it's including if it's the fundamental RMS or and the power factor, what is it? How is it calculating the power factor? Because you basically said if they're using RMS, the power factor would be lower with the harmonics, right? If they had harmonics.
That's correct. Yes. Yes. So to answer your first question on sizing, great question. You can look at how much your harmonic content is, and based on that, you can order, like the ComSys active filters comes in 110 amp modules. So they've got a cabinet that'll hold 3, so you could put in 110, 220, or 330, and then you can add more. You can cascade them all. But what's interesting is your total current doesn't necessarily decrease, but we clean up that because the filter obviously needs current, and then when we inject that, it cancels out. So you end up with about the same as you started with. So it doesn't really add additional kW to your system. But so that's your sizing question. If I know what the harmonics is, we can calculate how much we need because all those current values are there. Your second question on power factor is a good one. I'm under the assumption that most meters probably are looking at RMS. You can actually set it up, a lot of meters, to say, I want to look at fundamental or I want to look at RMS. But if they don't tell me, I'm going to assume it's probably RMS. But like we're the post-Glover reps, as you know, and with neutral grounding resistors, I've had issues and we had to go back and actually change it from looking at the RMS current to just the fundamental. So, yeah.
Good
So,
stuff.
yeah, you need to know, you got to look at the meter and see when it's done. But most, I believe, are looking at RMS, especially if they give you harmonics. If they're giving you a harmonic value, then they got to be looking at RMS.
Gotcha. Any other questions from the group?
Looks like Mr. Carpenter's got a question. Sir, is that old or is that new? Or do you know?
I think it's all old. I'm looking at it. I have another quick question.
Bill, do you have
When
a
you're
question?
doing the
Huh? Go ahead, Colin.
when you're doing the analysis, how long do you typically recommend to sample the data or install the mobile power quality meters?
My recommendation, Carlin, is we put the meters on for a month. The way the reports from because I've looked at several different people that generate reports, they all end up generating the report based on a week worth of data. Because if you look at a month worth of data, it just burps. It's just too much data. Because I'm taking 128 samples per cycle is how fast I'm taking it with this meter. So the meters basically grab a week's worth of data and do the analysis based on that.
Got it.
But my recommendation is we put the meters on for a month.
Fantastic.
Any other questions? Okay. Well, I appreciate everybody's time. We're right under an hour. I like to see that. If you have any questions, feel free to call us. We're here to help you any way we can. Thanks and have a great day. How do we stop the webinar? That's the question.